Aha, there it goes. Oh, so it was you. Okay. Okay. All right. All right. Okay. All right. We are now recording, and let's get set up from the current slide. And my memory is we didn't go over safety, did we? We got everything else covered. Can't remember. I don't think we got started. Sorry, this will take hopefully not too long, but it's things you need to always think about. But before I say that, let me put this one in. I got yesterday afternoon from the people. I had asked for it last week. They finally got it to you yesterday afternoon. The class code for this course. Okay, so if you want to jot it down, I will jot it down right here too. I'm going to send you an email with it on it. I just didn't have a chance this morning to do so. But it's the class code, so you can access your book and everything else, is Lawson.al. Then it's 8 digits separated. Now, they have spaces between these, so I'll try to put it like they did. 2709, and then 2966. I don't know how important the spaces are, but they had a space between the AL and the 27, and a space between the 09 and the 29. Can I get your name, please? Okay, got you. Okay. All right. Now, no input. Okay. Oh, you know, I don't know what's wrong with this system. Just because I don't have the wire done, it's still not coming on. And you would think it would have enough sense to know that I really wanted it to be on. Okay? Pardon me? Oh, okay, okay. So, this technology, it's just enough to drive you crazy, isn't it? Okay. They're all taking me seriously, okay? This is a problem, Houston, okay? I thought I was all set up and ready to go. I forgot that. Ha! There we go. So there, folks, for those who just came in and others, there's the class code for this course, so you can access everything on that Cengage Unlimited for this course. Lawson, LAWSON.al, and get your name, please. Say it. Ryan. Got it. Well, that pen won't work on that. Okay, there we go. Ryan Edwards. Okay, good deal. All right. For those who just came in, the class code for this course on your Cengage Unlimited is Lawson, LAWSON.al, and then in my thing they had a space, 2709. I've left off a 6, didn't I? Okay. 2966. Okay. All right. 2709 space 2966. Okay.
Do it matter if you use it by the book?
It doesn't. It's up to you. Some people like to have a book. Yeah. Here's what I would gauge it on. If you, where you either live or study or whatever, they'll always have consistent internet or very slow internet or something like that. I would think a book would be helpful. Okay, if you say go to the park to do your work, you know, or something cool like that, then you may not have internet access there. And even JT is here. Okay, so got it. All right, and for those who just came in, the class code for this course is Lawson.al space 2709 space 2966. Okay? So that would be my thing. Say we have a place over in Georgia, way out in the country. It's on the farm where I grew up. And when we go over there, the internet is so incredibly slow. And if my wife's on it or guests are on it or something like that, then it gets even slower. And I would want to have a book if that's where I was going to be doing. So that's what I would gauge it by. Other people just might like having a book, you know, a thing to have in your hands. And so when you're on the bus or when you're in the doctor's office, say I do a lot of stuff when I'm waiting for doctors and stuff. I can always do it. And sometimes at the Clarkin Clinic, I cannot get on the internet. It's just too many people get on it, and there's no room. So it's up to you. It's only $8, so once you're in the system. All right, now we had to deal with safety. And the first thing I noticed about this room, I don't usually teach in this room, there is no map of where the closest exit is. Okay? Now let me see where the closest one in the hall is. Right outside the door here, turn this way, turn to the left, and just past the first office, which is just next door on the other side of this glass, you'll see an outline of the building. I mean, of this floor anyway. Okay, and on that, that would indicate where the closest exit is. And you need to know that for safety purposes. So what 3 areas of safety do we always need to keep somewhere in the back, front, somewhere in your mind to have an idea of what to do in case an emergency happens? You don't have to say, what do we do? You know, have it in your mind. What? Say again? Okay, my hearing is so bad. Say again? I'm hearing is bad. Oh, okay. Okay. That you might do, yes, in one of the circumstances. What circumstance are you talking about then? 3 areas that you need to think of safety. I know what you're thinking of, don't you? You're thinking of active shooter. That's certainly one area of safety. And that's the one that I have the most problems with for this classroom. Okay? And I think I'm going to come up with a solution for it. And here's what my problem is. You see this door here? There's no way you can lock it from the inside. Okay? There is no button on the jamb there that you can push and lock it even with a jar. You have to get outside the door and lock it from the outside with a key. And guess what? None of my keys work. What? But. I do have a key down in my office that used to work on this door, and I'm going to check it out and see if it does work. And if it does, I was trying to think of the best place to put it. I'm thinking of taping it right up here. So anyone who's in this room, should that situation occur, which we hope will never occur at this place, but if it should, the key will be right up here. Now, none of you are so height challenged that you couldn't reach this, can you? I could put it here, but I'm afraid it'll walk off there. Can everybody? I think I'll be the only one that needs it, so I'll tell the other instructors to use it. I'm going to tape it right there. Then I'll take that key and go outside here, lock the door from the outside, and don't you pull it too, okay? Then I'll come back in and pull it too, okay? So I will be doing that. Okay, let's start over again. Active shooter, is that what they call it? Yeah, active shooter, okay? Guess what? If there's a pop, pop, pop somewhere because I'm hard of hearing, you will hear it before I will, okay? So you let me know. Stop me in my tracks and tell me, whoa, stop. That sounds like gunfire. Okay, at that point, I start working on the door. What do some of you do? At least one.
You start throwing tables at the door.
Okay, wait, just a second. Say again? Okay, 911, or actually a better number than that is campus police. Does anyone know the campus police number? You do. Okay, excellent. Okay, it's in your phone. That's right where it ought to be. So I'm going to put that on here too. What's the campus police number? Are you? What's that? Okay. 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 What's that number? Okay, it's on the website, but we don't have time for that. You need to have it on speed dial on your phone. I don't have my phone with me, so I can't tell it to you. But actually, someone told me the new Lost in State app that you can get, it pops up right on top of that. Okay? Does anyone have it? Well, get it. Look for it. And put it in speed dial. If you don't have it, 911 is next best. Because you see, campus police are here. Okay? 911 is going to take a few minutes to get here. And as soon as campus police gets the word, they will contact 911 because they have a hotline directly to them. So they're really the best number. So that's a good thing. 911. As soon, or campus police better. As soon as that phone call's made, what do the rest of us do? Turn off our phones so they don't make any noise at all. We don't want any incoming calls. No noise. Okay? So turn your phones off. Okay. Now, I've got the door secured. You've called the police. We're going to turn off the lights so it looks like nobody's in here and the door's locked. And where do we go? Over here. Excellent. Everybody get along this wall out of sight from that window, because you can see in the window, he can shoot through the window. He may even be able to shoot through the door. I don't think he can shoot through the concrete block wall. If he does, then he's standing right there, and the flashback is going to really hurt him more than it does us. So we all get over here, and we remain very quiet. That's our flight. Okay. Now, if somehow he managed to get in, then maybe we'll do the, what was the second one? Fight. Leave the fighting to me. Okay? Because your lives are ahead of you. Mine's back here somewhere. Okay? So I don't have as much to lose as you do. So let me do the fight. Okay? Didn't you have three things? Run, fight, flight, no, what was it? Run, hide, flight. Okay, we're not going to run, we're going to hide first, so we can lock the door. I'm going to get the key up here, hopefully today, and put it up there. I'll check and make sure it still works. It's the old key, I think it'll work, okay? And then we hide, and then we're very quiet. Okay, so that takes care of active shooter. Hopefully it'll never happen here, but we got to be prepared and think about it. What? Okay. Usually that office is locked, but if they do get in and go through the window, we're still back here, we're better. If that gun comes through the window, I'll try to get over here and do something with the gun. Get it to point that way, okay? And yank them through the glass and try to cut them up as much as possible. Okay? I'll get vicious then, okay? And if I get debilitated or get in a struggle with them or something, and you want to help out, this sounds gross, but believe me, folks, I think this is the best thing. Go for the eyes. If I got him down, go for the eyes. If he can't see, he can't shoot us very well, okay? I was in the Navy, and we had, at least once, it seems like a couple times, we had Navy SEALs that traveled with us across the Pacific, and they were nice-seeming guys, but you wanted to stay on the good side. I'll put it that way. And I was standing watch one night with one of them, really nice guys. They wanted to stand watches with us and do all this kind of stuff, so we were up there, and the petty quartermaster who kept the log and stuff, he just wanted to talk with this Navy SEAL. Hey, I bet you don't worry. If you're in a bar fight, you know you're going to be on top. He said, hey, look, the last thing I want to be in is a bar fight. He said, our training has that we control as much of the situation as possible, and therefore, if I see a bar fight breaking out, I'm out of there. The run, okay, the flight. He said, I'm out of there. He said, oh, but what if they got you cornered? I know that you know what to do. He said, I still try to get out of there. I may create a distraction. He said, it only takes a few ounces of pressure to take your little finger and pop someone's eyeball out. And while he's figuring out what to do with that, I get out of there. I know, isn't that gross? So that's why I say, go for the eye. And then he said, and if that doesn't work or you can't get to the eyeball, it only takes about 2 or 3 pounds of pressure to pull off someone's ear. Hand it to him, and while he's trying to figure out what to do with it, get out of there. Okay, now that's a Navy SEAL. So, get the guy, okay. If that gun does come through here, I'll do everything I can to get it pointing that way. And like I said, yank him through the glass or whatever it takes. And if you do get involved, go for the eyes. Can't see, can't hurt. Okay. I'm sorry, that was probably way too gross. Okay? But it was fun. Oh, never mind. Okay. Now, second safety issue. Doesn't matter the order. What's another safety issue? Fire. What if there was a fire? Let's start with the worst case scenario. That it starts in this room. Let's say my computer explodes, okay, or one of these electric outlets do, or the projector there, and starts arcing and sparking. What do we do? Okay, that's a good idea. We get out of here and everybody else burns down, and we say, oh, wait. Oh, we got to pull the fire alarm. Yes, we need to think of that too. We need to run, you're right, but we need to think of the other people in the building too. So the big question is, where is the closest fire alarm? You're absolutely right. Nobody knows on this floor. This is the old part of the building built before fire alarms were on the code. So to get to the closest fire alarm, okay, when you go out of this door here, you hang a right. You see an exit sign right there, just a couple doors, hardly a door down. Okay? Go down a half flight of stairs, go to the new student services entrance. Okay? That new part, don't go toward the bookstore, go toward the left where the offices are. And you'll see on those walls fire alarms. So that's a good thing to do. And I would suggest 2 people go in case one trips and falls. The other one can still go there. So go on the buddy system and head to the fire alarm. Okay? What's another thing we need to do? Yes?
Call 911.
Yeah, absolutely. While somebody's doing that, and again, campus police are the better choice. 911 is backup. Okay? If you don't have the campus police on speed dial, then do 911. Okay? I was looking for the next thing, okay? One other thing, especially if it started in this room. We're just going to let it burn. Yay or nay?
Yeah.
What do we do? Closest fire extinguisher. And where would that be? All right. Now that one there is on this hall. When you go out of here, hang a left. Right is to the stairwell. Left is to the fire extinguisher. Right at the end of the hall, just not more than 25 feet from here, you'll see it right there. And I know some of you guys, and maybe you gals too, have always said, "Oh, wouldn't it be so cool to break that glass?" Yeah, I knew some of you thought that. Okay, but you get your chance then. Go break the glass, bring the fire extinguisher. I'll take care of trying to deal with it, and the rest of you go out in a very orderly manner. And where do we go? Outside the building. And what's the nearest exit? This time you go out of the door, hang a right, and that exit sign there is just a few feet away. Take a right and go down 1 flight of stairs and head out the front of the building, right toward the hospital. Now, some of you think the front of the building's back there, and that is the front of the building, but the one toward the Bessemer Superhighway and the hospital. Go into that parking lot and stay there. Stay there as a group. I'm going to be the last one out of here. because I'm going to make sure whoever the slowest student is, in case you have a bad knee or bad ankle or something like that, I'm going to help you down the stairs. I'm going to go and I'm going to take the roll. I'm going to be in a roll book by then, hopefully, but hopefully it'll never happen. I'll take the roll and a pen and I'll call roll from down there. And if you are missing, you've wandered off, or you say, hey, fire, school's over, I'm out of here. No, don't do that, because if we can't account for you, myself or some fire professional is going to have to come into the building, a burning building, and search for you at risk of our life and health. Let's not do that. Stay together. The ones that went to pull the fire alarm, come back and join the class. The one that went to get the fire extinguisher, head that way. We all go together, and the last one out, we call roll. They'll let us know what to do. It may be a minor thing. Okay. Now, if we just hear the fire alarm, all we have to do is worry about getting out of here. Follow that path out. Okay. We do it safely. We don't run. We don't push. We don't shove. We go in an orderly fashion. We don't poke, but we don't run. Okay, any questions? What's the third? Second? Yes, weather emergency. Now, I've not heard it from in here because this is an interior room. If you hear that alarm go off, it's usually Wednesdays at what, noon or something like that. It goes off 11 or something like that. We won't be in here, but if you hear at a time other than that it shouldn't be going off, that means there's a weather emergency. It could be tornado, that's the worst. It could be severe thunderstorm, wind, rain, stuff like that. If we hear that, where do we go? Say again? Okay. The best hallway is low and interior. Okay, we're up on the second floor. Let's get down to the first floor. Let's get as low on the first floor as we can, and then we stay interior. The hallways are pretty good because the walls are relatively close together. This room, for instance, even though there's no outside glass or anything else, the ceiling could come down, okay? A tree could fall over, anything like that. Not the best, okay? So down, low, interior, that's what you think. And we stay together. And again, I'm the last one out, following the slowest student, making sure everybody's out, taking a roll. We take a roll when we get down there. And once we have the roll, if you want to go around, mingle with friends, find an interior classroom to take a nap, I don't care what you do, but you don't leave the building. You do not leave the building. The worst place to be in a severe weather situation is on the road. So don't worry about the cat being outside. Cats will take care of themselves, okay? Low interior, okay? Any questions? Okay. Now back on the fire thing, and that also, the fire also pertains to chemical spill, noxious fumes, something like that. We get at least 25 feet away from the building. That parking lot is awfully close to the building. I'd say we go down the hill a little bit further away, because if there is an explosion, glass is going to be shooting that way, and we don't want to be within range, okay? Any questions about safety? Sorry about that. That probably took too long, but I want you thinking about it. All right. And for any who came in late, there's a class code. And campus police, I never got a number for them, but y'all can get that. Okay. All right. Let's finally get started on math. Okay. Chapter 1 is functions and their graphs. Sections 1.1 through 1.3 are basically reviewing 1.1, the rectangular coordinate system. You should know all about that. If you don't, review 1.1. If you have any questions, ask me, okay? Second, graphs of equations. Again, that's something you should have had in an earlier math course, high school, somewhere else. If it's a little rusty and you're not sure about it, ask me, okay? Review 1.2. And 1.3 is linear equations in two variables. Again, that's something you should have had in earlier courses. We're starting today, and if you remember, on the course description, it said this course covers the algebra of functions. So that's where we're starting in 1.4, functions. Okay? Our objectives here are Determine whether relations between two variables are functions. They may not be. And use function notation. And you're probably already a little familiar with it. If not, it's pretty simple. We will find the domains of functions. New word there. Some of you may be familiar with it. If you're not, it's a fairly simple concept. We'll use functions to model and solve, real-life problems, and that will be fun stuff to do. And then we'll do something called a difference quotient, okay? And you've already done that before. You probably just called it something else, okay? So that won't be new. Let's see if there's some more. Nope. So let's start with introduction to functions and function notation. Many everyday phenomena involve two quantities that are related to each other by some rule of correspondence. Okay? Let's say your birth date and your height. Okay? That's two phenomena, but really, are they related? Not very much. So that may not be a function. Okay? How about age and birth weight? Not birth weight. Age and weight. Some of you may not want to give it. I don't. But anyway, actually, in your formative years, there's a really good relationship there. The older a kid is, generally the more it weighs. It's going to gain weight as it goes. Now, when you get my age, you don't want that to be continuing, and yet it does. You know, so yeah, there may be. So that's a relationship between two entities. That is a relation. Some of those are functions, some are not. Okay? In mathematics, equations and formulas often represent these kinds of relations, and most of the time those will be functions. Not always, but most of the time they will be. A lot of times they will be. For instance, here's a very simple one. The simple interest, okay, I earned on $1,000, wish I had it, for 1 year, if I could hang on to it for 1 year, is related to the annual interest rate, R, which today is pathetically small, okay, by the formula I is equal to 1,000 R. Hey, there's a relationship. The higher the rate, the more interest I'm going to get at the end of the year. The rates as low as they are now, I'll get a few, no, you'll get a few dollars, but not very much. Okay? So yeah, that's a relation. And it's also a function. Because as R goes up, so does I. Okay? Your interest rate, the amount of interest depends on the rate of interest for a fixed amount of investment. You know the bad news? It also works the other way. Credit cards. The more you have on the credit card bill, the more the interest you're going to be paying. Okay? If you don't pay it by due date. Okay? And I tell you what, that R is a lot bigger than the savings R. The savings R is minuscule. Maybe a fraction of a percent right now, 0.5%, 1/4%. What it is on your credit card, sometimes as much as 24%, 25%, 18%. Big difference there, folks. Now, I remember when we got married, my wife had credit cards. I had a few, but didn't use them very much. But she said, don't worry, I'll pay it. I make the payments every month. I'll make the payment. Well, at the end of the year, when we were doing our taxes, and we saw the interest that she had paid on the credit cards, she said, yeah, but I paid it all off. I paid it all. I said, I know, but look at this. I'm just going to make up a number. Let's say $125. It's $125 you paid to the credit card company. If you hadn't, you could have bought $125 more stuff. She went, oh, yeah. She started zeroing those balances, and as far as I know, we've never had a balance since then, you know, because she decided she'd rather pay for stuff she wanted than paying the interest on the credit card. So it works both ways. Same formula works, only their R is much bigger than ours. Okay, savings R. Okay, that was a little advertisement. Okay. The formula I is equal to 1,000 R represents a special kind of relation. It is a relation. I is related to R, It matches each item from one set, the interest rates, to the other set, the amount of interest, okay, with exactly one item from the previous set. So let's say, just for funsy, the R was 1%. Okay, 1% of $1,000. You want to do that in your head? $10, right? At the end of the year, you got $10 interest, okay? If that was 2%, what would you have? 20, okay? So you see, every R that you put in there is going to give you one and only one I on the other side. That's what makes it a function. Such a relation is called a function. If for any item on the input side gives you exactly one answer on the output side. So here's the definition. A function f from a set A to a set B is a relation that assigns to each element x in set A, it doesn't have to be x, it could be r, in set A, exactly one element y, or in this case I, in set B. That set A, all your possible inputs, okay? Now right now the interest rates probably range from 0.25% maybe up to, on the savings side, probably no more than 3 or 4%. If the very best rates I've seen out there would be that. And those would be maybe a little on the risky side. I don't know. But anyway, that would be the set A. All those possible interest rates are. Okay? The set B would then be the output. How much you're going to get from that. And that could be any number. Okay? Depending on what your principal is. This happened to be 1,000. It could be 10,000. Yeah, dream on. 100. Okay, that's more likely. Okay, it could be anything. But the input is called the domain, the set of inputs. The output, the I over there, is the range, set of outputs. Okay? So there we have definition for domain and range. Okay? Usually in a formula, okay, or equation like that, the thing standing alone is usually the output. The thing that's over here mixed up with the other numbers, that's the input. Change the R, you change the I, okay? The input, and we also call that the independent variable. You pick your R, you determine the I depends on the R, right? So I is dependent, R is independent. Don't worry about that, we'll get there later. All right, this is called a mapping of a function. To help understand that definition we just did, let's do this function. You think this would be a function or not? It certainly is a relation. The time of day for any given day, okay, today say, time of day from 1 to 6 in the afternoon, and the temperature. Do you think at any time of day there are multiple temperatures out? Now we're talking about here in Bessemer, Alabama, on the thermometer outside the window somewhere, okay? That at any time of day, and you look at the thermometer, how many temperatures are you going to see? One, and only one. How can you see two temperatures on that one thermometer? You know, it's only going to get, huh? It's broken. Okay, exactly. Okay. All right. But if a good thermometer at any time of day, there's only going to be one temperature. So that's going to be a function. Okay? Now let's notice some things there. At 1 o'clock, it was 9 degrees Celsius. Who reads Celsius anyway? Okay. That would be about about 50 degrees, a little bit less than 50, 47, 48, something like that, okay? Not this time of year, not here in Alabama, okay? Maybe somewhere else, okay, at a different time of year. Okay, 2 o'clock, it went up to 13 degrees Celsius. I'm not going to do any more calculations like that. 3 o'clock happened to be 15. At 4 o'clock, wait a minute, it was still 15. Can that still be a function? Yeah, because at any time there's only one temperature. You could have the same temperature for multiple times, especially if you're in a temperature control environment. You hope that to be the case. But at any one time, there's only one temperature. 5 o'clock, it had finally dropped to 12. 6 o'clock down to 10. Yeah, that's a function. And that's called a mapping diagram. Notice we used every input value. We only did hours 1 to 6. There were many other temperatures that could have been here, so we didn't use all the output. The domain was what? The time. And there are times 1, 2, 3, 4, 5, and 6. That's the only ones we looked at. Okay? The range, any temperature it could have been in that location that time of year. And it could have been anywhere in there. Okay? So, set A is the domain, set B is the range. The outputs we used were only 9, 10, 12, 13, and 15. Okay? You don't have to list them in that order. You could have done 9, 13, 15, 12, and 10. But it could be that you don't need to list the 15 twice because it's 15. That's all it is. You just happen to use it twice. Or 15 times, or 3 times, or whatever. Okay. Does that make sense? Okay? Now, here's another way we can represent a function. Sets of ordered pairs. Now, when we say set, we designate set by these little, they call them a brace, that little curly Q looking thing. That indicates it's a set. What this is a set of, the elements of that set, are ordered pairs. Ordered pairs are pairs of numbers set apart by parentheses. That's an ordered pair. Now later we'll see something else that's set apart by parentheses. You just have to know by context whether you talk about ordered pair or a interval. But we won't mess with intervals yet. So these are ordered pairs, and these are saying the very same thing that mapping diagram did. At 1 o'clock it was 9 degrees Celsius. At 2 o'clock it was 13. 3 o'clock it was 15. 4 o'clock it was 15 again. 5 o'clock it was 12. 6 o'clock it was 10. So that's another way to express that same function. Express it as a mapping. Express it as a set of ordered pairs. Okay? So, what are characteristics of a function from set A, time, to set B, temperature? Each element in A must be matched with something in B. If it isn't, that's not going to be a function. If there was no temperature over here that time could have had, that means probably the sun just exploded or something, and no, we're dead anyway, so who cares? Okay, no, okay, we won't go there. Okay, some elements in B may not be matched with something in A. We had temperatures over here that at those 6 times didn't happen. 1 degree, 18 degrees, and a few others in there. Okay? 2 or more elements in A may be matched with the same element in B. Perfectly fine. There were 2 times that were at 15 degrees. That's okay. But you just couldn't have 2 temperatures at any one time. That wouldn't be a function. An element in A, the domain, cannot be matched with 2 different elements in B. Let me give you maybe a more a practical example that I think you could probably relate to. Let's say you're down in the bookstore, okay, and you've decided to buy you a bag of chips, okay, and the person in front of you had an identical bag of chips, okay, and that person went through the cash register and they paid $1.19 for that bag of chips, and you put yours on there, you watched them pay, you heard them that, they left, and then you went and put the identical bag of chips down there, and they charged you $2.19. Would you be a happy camper? Probably not, okay? Because for the same input, there were 2 different outputs. That's not a function. That's arbitrary and capricious, okay? It's not a function, okay? So you can't have any element in A having more than one element in B, okay? So we've talked about 2 ways to express functions. Here are 4 ways, common ways to represent functions. 1, you can verbally, by a sentence, describe how the input variable is related to the output variable. I sort of did that with child's age and child's weight, okay? I could explain that in a sentence, and that would probably be a function, okay? At any age, the child only weighs one amount, okay? It'd be cramming its face while it's on the scale. You know, we don't allow that. Okay. Okay. You can do it numerically, and that could be a table or a list of ordered pairs. We solve the list of ordered pairs. Sometimes we do those in tables. Sometimes if y'all did graphing somewhere, you probably did T-tables. You put the input here, the output there. You put the value for X here, and then you had the function Y here. You calculated based on what X is, what the Y's got. You've done that before, haven't you? Now, you can do those tables horizontally. Most of the time, I think I'm vertically, but you could do them horizontally as well. I like going horizontal most of the time, but no, for tables, I like vertical. Okay. Graphically, now we haven't done that one yet. We'll see one coming up soon. Points on a graph. Well, you did it. When you did those T-tables, then you plotted those points, didn't you? So you did, whether you knew it or not, you were graphing a function, or it could have been a function. Okay? So graphing the points on a graph on coordinate plane in which the horizontal, now here's the key, the horizontal axis we always call the, okay, the whole thing's a plane, but what do we call that horizontal axis? We always call it the x-axis. It doesn't have to represent x, it could be r, it could be t, it could be anything, but it's a horizontal axis. That's the independent variable. That's where the domain is located, on the horizontal. That's the input. The output is the vertical. We always call that the y-axis. It doesn't have to be y. It could have been I. It could have been weight. It could have been whatever. Okay? So we could represent it graphically. You've probably already done that. The vertical represents the output values. Or you could write it algebraically as an equation. I is equal to 1,000 R. There it is. There's your function. Okay? Make sense? All right, good deal. I don't know if this is helpful to you or not, but it was helpful to me. I think it was the very first time I had really heard the word function being thrown around. It was in my Calculus 1 class when I got to college at Georgia Tech. And I had never heard the term function. We'd never talked about it in high school, ever, okay? And the professor used this illustration. He said, think of it as a black box. And he drew the box here, okay? Okay? And the box has a crank on it. And he said, you put stuff into the box. That's the input, the domain. You turn the crank, it does something to that stuff, and it spits out the output. The input was one thing, the output was something else. The function is what did the change. And as soon as he did that, lights went on in my head, because I grew up in a farm in Georgia, okay? And we used to kill our own pigs. Okay, we raised the pigs, and coldest day of winter, they would try to do the hog slaughter. Okay, and this was when I was fairly young, and I would watch all this stuff. I was too little to do very much with it, but I would watch them do it all, and they would get the meat inside, and my dad would start cutting it up. The pork chops, the ham steaks, the bacon, all the things, but all the time he was doing this, he had a scrap pile over here. Anything that, little streaks of meat that didn't fit in anything, he just put in the pile, put in the pile. Little hunks of meat that didn't fit, put in the pile, put in the pile. At the end, he packaged up all the other, and then he brought out the sausage grinder. That was my job. I got to turn the crank on the sausage grinder. So as soon as he did this, I pictured. There were the scraps of meat were input. We put in peppers. We put in spices, sage, and other stuff like this, put in whatever they wanted to do to flavor it. I turned the crank, and out came sausage, okay? Input was the meat, the spices, the peppers, whatever we wanted to put in there. Output was the sausage. So I thought, ha, I can understand that. That's what a function is, okay? That probably makes no sense to you whatsoever. But you haven't lived. Okay, never mind. I didn't say that. All right. And boy, we ate well that night. Okay. So let's see. To determine whether a relation is a function or not, you must decide whether each input is exactly matched with only one output value. That's what it takes. If it's not a function. If it looks like it is, it probably is a function. Now, you usually can't check every one, but there are some ways you can do this. When any, I hope that's not my phone because I'm too far away from it. Okay. When any input value is matched with two or more output values, not a function. Is a relation, but not a function. Okay? Now, let's get where we are in the book. If you have a book, we're on somewhere about example 1, and there it is. So let's determine whether each of these relations, y, represents y as a function of x. There we go into our favorites again. Y is the output, x is the input. So here's the A example. The input value is the number of representatives from a state. The output value, y, is the number of senators from the state. Okay? Would that be a function or not? Weird example, right? The input is the number of representatives from a state. The output value, y, is the number of senators from that state. Is that a function or not? Oh boy, I hear the gears I see the crank turning and the gears are grinding, but they're a little rusty. They're making noise. What you think? Function or not? Don't think so. Why? Okay, you're absolutely right. There's only 2 senators from each state. So you're saying that different number of states with different representatives can't all have the same number of senators. Yeah, but guess what? Does anyone know how many representatives Alabama has? It's either 7 or 8 or 9 maybe? Huh? You think it's 9. That sounds reasonable. Okay? 9. And how many senators do we have? 2. Okay? We don't have 7 or 3 or 2. We just have 2. So for every input, there's one and only one output. California? Oh no. Hundreds? Okay. But they have 2. New York? Bunches. Wyoming? 1 representative, but 2 senators. So the number of representatives, it doesn't matter because the number of senators is constant at 2. Nothing but 2, only 2. That is called a constant function. Because no matter what you put in, the output is 2. And that's the only number you get out. So it's basically got to be a function. Now, if it was that, oh, well, small states can only have 1 senator. Well, then, yeah, you'd have a problem, okay? But it's not. Every state has 2. So that actually would be it. It doesn't seem like it would be, but it would. No matter what the number of input is, number of representatives, there's 1 and only 1 output, and literally 1 and only 1 output, 2. Okay? Now, the B one. There are inputs, and there are outputs. X is on this is sort of like a T-table. Is that a function or not? Why not? Yeah, you put in a 2 one time, you got 11 out. Put in a 2 again, you got 10 out. That's you know, the grocery store, you know, the bag of potato chips. No, don't want that one. Not a function. Okay, here's one that's a graph. Now this is a graph, and by the way, they call this a discrete graph because it only has certain points. Okay. There's also could be a graph that would be continuous that connected those points. This one's discrete. Where would be the inputs? You tell me the, okay, tell me the inputs for C. -2, -1, say again, 0, 1, and 2. Those are the only 5 inputs there. We pulled those off the horizontal axis, you see? This one up here was at -2, this is -1, that's at 0, this is at 1, this is at 2, and those are all. That's it. Those are the inputs. Is that a function or not? Yes, it is, because every one of those has 1 and only 1 output. 3 for -2, Negative 1 has the output of 0. 0 has an output of negative 1. 1 has an output of. Can you have that? Can two inputs have the same output? Yes, no problem, as long as it's just 1. Okay, and then 2 has an output of 3, even though negative 2 had an output of 3. Now, for a graph like this, there is an easier way, and I'm going to jump ahead and tell you what it is. When you have, say again, vertical line test, excellent. You can draw any vertical line. If a vertical line crosses that graph more than once, not a function. Okay? So that's another way, but we haven't gotten there yet. Okay? Good idea, though. All right, so let's look at that. That verbal description, that was one way to describe a function, does describe y as a function of x. Regardless of the value of x, the only output is 2. Okay? There's only one output for any x you put in there. It just happens to be they're all 2, okay? That's called a constant function. Because no matter what the input is, the x value is, the output is always 2. And 2 states with the same number of representatives would have the same number of senators. Okay? So that is a function. Okay? This one, the table does not describe y as a function of x because the input value 2 had 2 different y values. Can't happen and be a function. Is a relation, not a function. Okay? And the graph does describe a function because each input value, negative 2, negative 1, 0, 1, and 2, only had one input value on that. Now, let me draw you a really nice function. Relation. There's a circle. Does that represent a function? No, because for any one input here, say this one here, you have an output up here and an output down there. Not a function. Certainly a nice relation, but not a function. Okay? That's not a very pretty circle either. Okay. So, representing functions by sets of ordered pairs is a common in what we would call discrete mathematics. I used that term earlier for that graph that only had 5 points on it. Discrete, numbered, countable. Okay. Okay? So sets of ordered pairs work well then. If you were doing, and if you did ages and weights in here, that would be discrete. It'd be a big number because we have, 32 or 3 people in here, maybe more. It would be a big set, but it's still discrete. Okay? Even if you did everybody on the planet, big, but discrete. But if you did, say, height versus weight, who knows what? The heights could be every fraction of an inch between any 2 things. You know, age, you're only a fixed age, but heights, so that's probably not a good example. But anyway, in algebra, however, it's more common to represent functions by equations or formulas involving 2 variables like this one. Y is equal to x squared. Is that a function? Yes. Give me an x. Any x. Give me an x. 4, 5, 4. If you put 4 in there, what's your y? 16. Exactly. And only one y. There's no other y who's 4 squared. That's it. 16 is it. Give me another x. Did I hear 5? What would be your y? 25. Give me another x. Say again? Yeah, you give me numbers, you're going to drive me nuts, okay? No. How about negative 4? 16 again. Is that knock it out of being a function? No, it's still a function. It's just because negative 4 only has one answer, okay? So, that is a function. But guess what? That's not discrete. Even though we chose discrete values, you could have 4.357 and 4.000001 and 4.999999999, which would be different from 5. So you have an infinite number of inputs and therefore an infinite number of outputs. So that would not be discrete. That's continuous. Okay? So you wouldn't do sets of ordered pairs for that. You could do a few like we picked out some, but you wouldn't get them all because there is no limit. Okay. So that represents a variable y as a function of the variable x. In that equation, which is the independent variable? The x, because I say, give me an x. You get to choose any x you want. That's independent. But once you choose the x, no choice on y. It depends on what x you put in. Okay? So that's the dependent variable. Y is the dependent variable. Let me see where we are here. Yeah, there we are. Oh, here's a handsome character. He must be a mathematician, okay? His name is Leonhard Euler. It looks like Euler, but it's pronounced Euler. Swiss mathematician. He had to have been one of the most prolific mathematicians in history. There are so many things that he did and came up with, and one of the things he came up with is what we're going to talk about next, function notation. He came up with the idea, let's call it f of x. Pretty simple concept, he came up with that, okay? Does anyone know what the number e is? It's an irrational number. It's 2.7 blah, 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 and you just keep going digits. They never repeat. They never repeat a pattern or anything. Just a random digits that keep going. Except there's a fixed, they're special digits, okay? And it happens to be the natural base of our number system. We think 10's the base. That's our counting system. But our number system, E is the natural. Guess why it's named E? Leonhard Euler was the one who said, hey, this is really our natural base. Now, I hope some of you make it to calculus. I know you will. I hope many of you do. And when you do, you'll find out why E is the natural base of our number system. It's the best thing to take a derivative or an integral of. And you'll find out it's wonderful. Okay? So, Euler came up with all sorts of things. There are several Euler equations or formulas and stuff, and some of them are so incredibly simple looking, but so profound. That guy, I mean, he literally, now this is before word processing, before any of this kind of stuff, he produced hundreds and hundreds and hundreds of papers, most of them groundbreaking. How did he do that in one little lifetime? And you know what? The latter part of his life, he was blind, and he could still do calculations in his head faster than his students could that were doing the writing for him. He was some character. Okay? I'm trying to remember if it was him. There were a couple that were similar to each other. That actually, his father was an accountant, and when he was like 2 or 3 years old, he said, Dad, you made a mistake. He didn't even know he could add or subtract or anything, and sure enough, he had. It may have been the other guy, Gauss. I don't remember which one it was. Let's do example 2. Example 2 is not in the set, I don't think. Let me see. Oh, no, this is okay, yeah. The domain of the function is a set of all values taken on by the independent variable. We already talked about that, right? The input set, okay? The range of the function is a set of all values taken on by the dependent variable, the y, the vertical, if you're graphing, okay? Just to say that again. Now, if you'll notice in your book, if those few that have books, it skipped example 2. So I'm going to go back and do example 2 right here. And this is pretty important because these examples always show up in the test bank, folks. So guess what? You'll probably see them on quizzes and tests, okay? Something like this, okay? What I'm asking you to do, or example 2 is asking you to do, and by the way, time out again. I think I mentioned to you early in the going, like when we're going over the course, how I really don't care for Cengage that much. That's the company that does this, Cengage Unlimited. I think it's a pretty good deal. I just don't like the company and their former way of doing business. But I like this author, Ron Larson. And here's one of the reasons why. This example 2, for those of you who have a book, you'll see it says, see larsonprecalculus.com. That's a free, open website. You don't have to be in a math course. You don't have to be anywhere. Anyone can go to that website. See larsonprecalculus.com for an interactive version of this type of an example. So even if you don't have a book, You can go to larsonprecalculus.com, and somehow it's organized. Go to section 1. Chapter 1, section 1.4, functions, and example 2, and you'll see this type talked about, expanded upon. That's one website he has out there absolutely free. I told you about the other two, calcchat.com and calcview.com. We'll talk about those a little bit later. He has more stuff out there than anybody else that I know of. Now, let me do a timeout here too. Remember I gave you that site for, the code? That code opens up for you WebAssign. Also, it enables you to access your book, but it also enables you to go to WebAssign. Now, have any of you used WebAssign before? Did you like it? Okay, yeah, it's okay. That's about the best I've heard from it. Some people really do like it. Some people, and some people, But there's one reason I don't care for it very much. They're looking for one and only one answer. Let me just give you sort of off topic here. But let's say you did a problem and you came up with the answer being 1/2 x squared plus 5. Okay? And you type that in as your answer. And they said, wrong. And then you go back and try to see what you did wrong in the problem, how you did your calculations wrong. You pull your hair out and you see, never mind, don't go there. Okay, but at the end of the day, and you come to see me, why is this answer wrong? And then I say, well, try this. And it says, right, good job. Guess what? Those are the same answers. Those are exactly the same answers. And you did it. You had a right answer, and it told you you had a wrong answer. It caused you frustration. It caused you griping and gnashing of teeth, and you had a correct answer all the way along. You worked and tried to see what you did wrong. You did nothing wrong. It was just as good an answer as that. Or vice versa. It could have wanted that one, and you put that one. So that's what I don't like. Computers really, I know there's artificial intelligence out there, and they're getting better, but really computers are stupid. They're programmed to recognize one and only. They think that everything's a function, and there may be more than one way to express an answer. It's the same answer, more than one way to express it. So that's why I don't use it, because I spend more time calming students down and tell them, no, you were right, that's a perfectly fine answer. It's just they were looking for this answer. Well, why? There is no reason they were looking for that answer. Actually, I can't say it for this course, but in trig, quite often y'all don't know this yet, the sine of 45 degrees, or pi force, is often it's called the square root of 2 over 2, which is absolutely correct. But sometimes the book will have that as the answer, and sometimes it'll be 1 over root 2. That's the same answer. Exactly the same answer. It's just that you multiply this one by root 2 over root 2. Root 2 times root 2 is 2. You have root 2 over 2. Those are the same answers. Exactly, precisely the same answers. And yet, it'll count one of them right and one of them wrong. And it's random which way they put it in there. Okay. So that's, to me, is why I don't mess with it. But guess what? With that code I gave you earlier, you have access to WebAssign. So if you like it and want to work some of those problems, the guy at Cengage put the problems in there. Work them to your heart's content. Check the answer stuff. If you can't get the answer they're looking for, see me, I'll help you. Okay? But here's the better thing, and this is good about WebAssign. It has tutorial help. So if you get stuck, then by all means use WebAssign and see if the tutorial help does you good. Are we out of time? Yes. Oh, how sad. Okay, we didn't get to do example 2. Let's see at the end of the section. Yuck, I'm sorry I talked too much. Okay, yes, you can do on page 44, if and when you get a book or on your ebook, any of the odds, either 5 or 7. Okay? Now, here's where the other 2 websites come in. Why do I assign odd number exercises? 3. Okay, the answers are in the back of the book. If you do that, it's either 5 or 7. If you do this is page 44, section 1.4 exercise. Okay? So if you do the problem, go to the back of the book, you get the right answer, go on to the next problem. Okay? Or skip a few and go to something else. Okay? But if you can't get that answer, and you can't figure out how they got that answer, guess what you can do? Look at the top of the page there. See CalcChat, remember I pointed that out before, .com, free website, anyone can go there for tutorial help and worked out solutions, folks, worked out solutions for the odd numbered, solutions to the odd number exercises. So there they are worked out for you. But not just that, okay? Number 7 is in red. And what does that mean? That means you can go to calcview.com and see even a fuller description of what's going on. So he has 3 websites out there. LarsonPrecalculus.com, calcchat.com with all the odd number exercises, and certain ones he has calcview.com. Now, here's a neat thing. This is called some sort of code. It's that QR code, a QR code. If you got a cell phone, you can just put on that. It'll go straight to calcview.com, and you can see it right there on your phone. Okay? Number 7, the ones in red. Okay? Now, you can do number 9. It's at calcchat.com, not at calcview. And then we'll wait and do the rest of them later. So I didn't get very much covered today, but from now on, it's all math. No more syllabus. No more research. I mean, you got that to do and stuff, but no more safety issues. We've got it covered. I'll put the key up there, and we will go from there. All right, good deal. We'll pick up in example 2 next time. Good deal.